Christy, you can hear my name, my sound, right? But you are muted, it seems. Please unmute. Now it's okay.
കേൾക്കാവോ?
ഇപ്പൊ കേൾക്കുന്നുണ്ട്.
ഒരു മിനിറ്റ്, ഞാൻ ഈ സ്ലൈഡ്സ് ഷെയർ ചെയ്ത് മൂവ് ചെയ്യുന്നുണ്ടോ നോക്കാവോ?
റെഡി.
ഓക്കെ. Share, where is share screen? You have to enable the screen sharing.
Just a second. Just a second. Yes. Now you try.
Okay. Share screen. Yes. Okay, now I am going to the PowerPoint. Share. And if I start the PowerPoint.
Yes, it's coming now.
Okay. Last time I had trouble with the slideshow. Now slide move ചെയ്യുന്നുണ്ടോ?
Move ചെയ്യുന്നുണ്ട്. റെഡിയാ?
Okay.
കുട്ടികള് എത്താനൊരു 7:30 മണിയാവും. 7:15 കഴിയും. 7:10 ഇവിടെ. റെഡിയാണ്. സ്ലൈഡ് റെഡിയാണ്.
സ്ലൈഡ് റെഡിയാണ്.
മൂവ് ചെയ്യുന്നുണ്ട്.
പിന്നെ വേറെന്താ? വരുന്നില്ല. ഒരു മിനിറ്റ്.
സാറ് വരുമോ? NC വരുമോ?
ചിലപ്പോ അറിയില്ല, ഞാൻ അയച്ചിട്ടുണ്ട്.
ആണോ? ഓക്കെ. സാറിപ്പോഴ് പിന്നെ റിട്ടയർഡ് അല്ലേ?
ഇപ്പൊ എമറിറ്റസ് 1 വർഷം കൂടി ഉണ്ടെന്ന് തോന്നുന്നു. ഈ വർഷം അവസാനം വരെ ഉണ്ട്.
അവിടെ AT-ലുണ്ട് അല്ലേ?
ഉണ്ട്.
ഞാൻ കുട്ടികളൊന്ന് ഇൻഫോം ചെയ്യട്ടെ.
എന്തോ?
കുട്ടികളൊന്ന് ഇൻഫോം ചെയ്യട്ടെ.
ഇല്ല. എങ്ങനെയുണ്ട് അവിടെ കോളേജിലൊക്കെ?
ഇപ്പൊ അവിടെ നമ്മുടെ കോളേജിൽ ഇപ്പൊ PG കിട്ടിയിട്ടുണ്ട്.
ശരി. ഇപ്പൊ സ്റ്റുഡൻസ് എല്ലാം BSc-കാരാണോ? അല്ലെങ്കിൽ
കൂടുതൽ സ്റ്റുഡൻസ് BSc-കാരാണ്. പക്ഷെ മറ്റുള്ള കോളേജസിലെ ഫാക്കൽറ്റീസും ചിലപ്പോൾ ജോയിൻ ചെയ്യും. 1-2 പേര് ഇപ്പൊ ഇവിടെ ഉണ്ട്. ഇപ്പൊ രമ്യ ടീച്ചർ, അതിലേക്കാണ് രമ്യ ടീച്ചറാണ്, ഫാക്കൽറ്റിയാണ്. ജെയ്സൺ സാർ നമ്മുടെ കൂടെയുള്ള പിന്നെ കൊളീഗാണ്. പിന്നെ 1-2 പേര് ഇവിടെ കാണുന്നുണ്ട്. മറ്റുള്ള കുട്ടികളാണ് ബാക്കിയുള്ള. ഞാൻ അവരെ ഒന്ന് ഇൻഫോം ചെയ്യട്ടെ, പെട്ടെന്ന് ജോയിൻ ചെയ്യാൻ വേണ്ടിട്ട്. ജസ്റ്റ് സെക്കൻഡ്.
Give a session in this webinar series. Then I welcome my colleagues, Dr. V.C. Sahir, coordinator of this webinar, and Jason sir. They took all efforts for making this webinar series come true. Once again, I welcome all of you to this webinar series. I invite our respected principal to inaugurate the webinar series. Please, Fatima ma'am. Fatima ma'am.
Fatima ma'am.
Fatima
I
ma'am.
think she's not here. Just a second, let me call her. Ma'am, please begin.
I invite our principal Fatima ma'am to inaugurate the session, webinar series. Fatima ma'am.
Ma'am, please unmute. Your voice is not coming up. No, your voice is not coming. You're not audible here, please.
audible now?
Yes, yes. Now it's audible.
All right. Thank you. Thank you, Dr. Lekha. Thank you, Lekha. I'm honored to be inaugurating this session, and I'm happy and delighted that the Department of Chemistry, which is a first PG department in the sciences, and they're organizing a series of webinars, and this is the first, as I understand, is the first of the series. And I'm really delighted that the department has such a visionary HOD, as well as enthusiastic and very proactive young teachers who would, I'm sure, steer the department and the students, the newly joined students, to a glorious innings. And this, I hope, is the beginning of this particular glorious innings. So we are happy and we are also honored that we have a resource person who is eminent. And I don't know anything about, let me confess at this point that I don't know anything about the topic. I don't understand the topic at all. But I understand that this series is actually the beginning of a series of talks, a series of webinars about the new aspects of chemical sciences, or new aspects in new directions in chemical sciences. And I'm sure that Dr. Sahir, the coordinator, would have chosen the best resource person to talk about this particular topic. And I am, on behalf of the college, I'd like to welcome Dr. Christie once again to this session. And I also wish the best for the department and for the series as well. Thank you very much. And I also officially declare the webinar open. Dr. Sahir, I understand that you will be giving an introduction about the speaker. Dr. Sahir, would you be giving an introduction, or shall I?
Yes, ma'am. Yes.
Yeah. Before that, let me officially invite Dr. Christie to deliver her address, and Dr. Sahir would proceed to give the introduction about the resource person, so that the students would also be familiar with her achievements.
Thank you, ma'am. Thank you, Fatima ma'am and Lega teacher. So it's my privilege to introduce my friend and our chief guest of the day, Dr. Christie George. She is an assistant research professor of Pennsylvania State University, USA. So let me give a few words about her. She is going to deliver a talk on dynamic nuclear polarization enhanced NMR, so part of spectroscopy. Before telling a few words about her, I would rather introduce Professor N. Chandrakumar, who is one of the renowned professor in the field of spectroscopy. I think he is also here with us today. And our chief guest, Christie, is Christie's professor. N. Chandrakumar sir is the professor of, Christie is the professor of N. Chandrakumar sir is the professor of Christie in her PhD, and after postdoc as a postdoc fellow. So I think he is also here with us, and we are happy that both of them are here in our inaugural talk.
Thank you. I'm happy to be here.
Yes, sir. Yes, sir. So let me introduce Dr. Christie with a few words. She is currently the assistant research professor, Department of Chemistry, Pennsylvania State University. She did her postdoctoral work at one of the premier institute in the world, Massachusetts Institute of Technology. and under Professor Robert G. Griffin. And she was a young scientist at IIT Madras after her PhD under the supervision of our dear Professor N. Chandrakumar sir. And she also she completed her PhD in NMR spectroscopy and imaging at Indian Institute of Technology under Professor Chandrakumar sir. And she did her MPhil in applied chemistry at Cochin University of Science and Technology, Kerala, and MSc also in MSc in applied chemistry at CUSAT, Kerala again. And about her achievements, she has got many publications, more than 20 very highly peer-reviewed publications. She got a Langmuir Prize for the Best Thesis Award in the Physical and Theoretical Chemistry at Indian Institute of Technology, Madras. And these are the few words about her. And we are happy that both of Christy and her dear professor, she's actually, and Chandrakumar sir is also my teacher too. He gave a course on NMR spectroscopy, and that was a breakthrough in my life actually, because he was actually one of the best teachers too. Apart from his research, he is actually one of the best teacher, and you can see his about him in his Wikipedia. So about our department, it's a webinar series, and there are many sessions to be held. And one of the session in this week is by Sangeet Das Kulathil. He's a research fellow of Queen's University of Canada. He's a former MSc student of IIT Madras. He will be giving a few talks to the students about chemistry in the modern era. And in the department, we are going to give a certificate course on applications of computer-aided designs in science, ACADS. It includes many sessions like in silico drug designing, coding science sessions, digital molecular designing sessions, deep learning and AI sessions, ab initio program design sessions, molecular symmetry machineries, and all these are included in our certificate course. And with these few words, let me hand over this to Professor Christy, Dr. Christy. Christy?
Okay.
Just a second.
Hello, can you hear me?
Yes.
Okay. I think I'm sharing the slides. Are you seeing my slides now?
Just a second. It's visible.
We are not seeing your slides yet, Christy.
Yeah, I'm sharing it actually. Sahir has to do something, I guess.
Just a second, please. Yes, you are a co-host. You can share it now.
Okay.
Yes, now it's coming up.
We are on now, yeah.
Okay. So first of all, I'll thank Sahir and all other organizers for giving me this opportunity. And thank you for being here, and thank you for inviting me. Sahir wanted me to talk about some research as well as some possible opportunities in US for students. So I'll talk about that at the end of the seminar. So first I'll present the research and also some basics of magnetic resonance. I realize that some of you may not be that familiar with magnetic resonance spectroscopy. So I tried to include some basics, but this may not be enough to completely follow it, but I'll try to make it as simple as possible. So I will be talking about dynamic nuclear polarization enhanced NMR spectroscopy. So first I will give a brief introduction to magnetic resonance spectroscopy. So as you all know, some of the nuclei have a non-zero magnetic moment associated with, it has a spin and associated non-zero magnetic moment. Such nuclei can give rise to a magnetic resonance spectrum. For example, if you look at the proton or the hydrogen nucleus, it has 3 isotopes and all 3 of them has a non-zero magnetic moment. Similarly, if you look at a carbon nucleus, carbon has carbon 12 isotope, which does not have any spin at all. Its spin is 0, whereas carbon 13 has a non-zero spin, which is spin half. So carbon 13 will give you an NMR spectrum, whereas the carbon 12 will not. So if you look through all the nuclei in the periodic table, at least for each one of them, at least one isotope is present which has a non-zero magnetic moment, and all such nuclei can be used for NMR spectroscopy. So all those nuclei which have a non-zero spin has an associated magnetic moment which is given by this equation. Now, when such a nuclei is interacting with a magnetic field, then the interaction energy can be represented by this equation, where gamma is a constant known as the magnetogyric ratio, and B0 is the applied magnetic field. And depending upon the spin quantum number, there can be, say if the spin quantum number is I, there can be 2I plus 1 energy levels. And for example, for a spin half nuclear, there can be 2 energy levels, which is plus half and minus half. Plus half and minus half. And the selection rule for NMR transition is that delta M has to be plus or minus 1. And when this energy level difference is dependent on the magnetic field, and it generally comes in the radio frequency region. So if we give an RF radiation, excitation happens from the low energy to high energy state, and the energy difference is given by this equation. So in terms of, if we rewrite this equation in terms of the frequency, we can write it like this, where omega 0 is known as the Larmor position frequency. And again, I want to emphasize that it is proportional to the magnetic field applied. Now, usually the nuclei are not bare nuclei. It is surrounded by electrons. It is surrounded by other nuclei. And hence this Larmor position frequency of a nucleus is modified by its local environment. And it can be written like this, where sigma is known as the shielding constant. Further, if there is a neighboring spin, that can affect the frequency, and this effect is usually known as the coupling. And if it is through bond scalar interaction, it is called J coupling, and the coupling constant is what is represented by the symbol J. And this equation includes both the chemical shift and the coupling. So what I'm trying to tell in this through this equation is that depending upon the chemical environment and the neighboring nuclei, the NMR spectrum will look different for each nucleus, for each sample. So here I'm showing 2 examples. One is the proton spectrum, proton NMR spectrum of 2,3-dibromothiophene. And 2,3-dibromothiophene, if you look at the structure, it has 2 protons next to each other, which are in 2 different chemical environments, and they are coupled to each other. So it gives 2 doublets. And if you go to some other molecule like 1,3-dimethylpropane, the spectrum will look like this. So the point I'm trying to make with all this is that even if you have a minor change in the chemical environment of a molecule, that will be well reflected in the NMR spectrum, either through the chemical shift and also through the coupling pattern, which you will be observing in the spectrum. So by looking at the chemical shift and couplings, we can identify the molecule. So the NMR spectroscopy can be used for structural characterization of molecules. Not only for structural characterization, it can also be used for the study of dynamics, etc. Now, depending upon the magnetic field, the resonance frequency is different. The chemical shift, either you can represent in terms of the hertz value, the frequency, but that will be different depending upon the applied magnetic field. So people generally represent this chemical shift as a relative value number, and usually it is represented in a ppm value so that it will not change based on the field. So either you can represent the chemical shift in hertz or in ppm. So depending upon the molecule, you will see a change in the chemical shift and coupling. And if you look at these lines, these are pretty sharp lines. That is the biggest advantage of NMR spectroscopy over other spectroscopic techniques. It will give you a really good resolution. That means very sharp lines, and usually these line widths are much less than 1 hertz. So the spectrum which I am showing here, these are generally known as 1D NMR spectrum. This is actually a 2D. I mean, like there are 2 dimensions. This dimension is the frequency axis, usually called the chemical shift, and it is represented either in hertz or ppm. And this axis is the intensity axis. But usually in NMR, we define the dimension based on how many frequency axes are there in the spectrum. So in this, there is only one frequency axis, so this kind of spectra are known as 1D NMR spectrum. Now, for simple molecules, it is good enough to take a 1D spectrum to identify the molecule, but sometimes that is not sufficient. As the molecule becomes more and more complex, you may not be able to distinguish or study a molecular structure just based on a 1D proton spectrum. By the way, it's not just proton NMR spectrum that we can take. We can have carbon spectrum, we can have silicon, phosphorus, fluorine, and you name it, a number of such spins. We can routinely collect the spectrum. Now, usually we have spectrometers ranging from 300 megahertz to 1.2 gigahertz. What we mean by that is the proton resonance frequency. So when somebody says that the spectrometer is 400 megahertz spectrometer, it usually it means that the proton resonance frequency at that field is 400 megahertz. The 400 megahertz actually corresponds to a magnetic field strength of 9.4 Tesla. At the same field, the carbon will be like 100 megahertz because the resonance frequency is also proportional to the gamma, which is the magnetogyric ratio, and it is different for different nuclei. Of all the nuclei present in the periodic table, tritium, the 3H isotope, has the highest gamma, but that's radioactive. So generally people are not using that for NMR. Among the other most common nuclei, proton has the highest gamma. So the spectrometer frequencies are usually referred by the proton resonance frequency. Now, when a 1D NMR is not sufficient to do the structural characterization of a molecule, we can do multi-dimensional NMR experiments. So here I'm showing some 2D NMR experiments. So if you look at it, it has 2 frequency axes in both dimensions, and the intensity is represented as contours. The higher the contour intensity, contour levels, more intense is that peak. And this kind of 2D NMR experiments can be used to map the structure, the bonding pattern or connectivity in a molecule. For example, this is a butanoic acid molecule, and of the 3, and if you look at this molecule, this proton, the CH3 proton, this CH2 proton, this CH2, and this CH2, these are all at different chemical shifts. But to in this spectrum, we can identify three separate peaks, which this particular three separate peaks. But if you look at the 2D spectrum, how do you analyze this? This is both the axes are proton chemical shifts in this case. And if you look at this peak, this particular peak has the same chemical shift on both dimensions. Such peaks which have the same chemical shift on both the axes are known as diagonal peaks. And the other peaks which are symmetric with respect to that diagonal, these are known as cross peaks, which will have one chemical shift in one of the axes and another chemical shift in another axis. And the cross peak which is coming between these two diagonals, which means that these two types of protons are coupled or are adjacent to each other in the molecule. So by looking at these cross peak patterns, you can find out which proton is next to the to another one. And by mapping that, you can find out what is the structure of the molecule. Like this homonuclear correlation, you can also do heterocorrelation experiments. That means you can correlate a carbon with a proton, and you can find out which carbon is attached to which proton. So there are a number of such experiments in NMR, like not only 2D, but also 3D and other higher dimensional experiments, which will help to find out the structure of molecules. So basically, NMR, all the experiments that I have shown so far were taken in solution samples. Now, NMR can be performed on solid samples also. But the problem in solid state is that the anisotropic interactions are not averaged out. What I mean by that is in solution state, the samples are tumbling all over the place, and many interactions, including the chemical shift, are anisotropic. So what we expect in a standard NMR spectrum is that if you have one particular chemical environment, you expect one peak for that or one chemical shift for that particular nuclide. But these interactions, if the molecule is rigid, the interactions are anisotropic, and instead of giving us one single chemical shift, the chemical shift can be spread over a range. And you will see that in solid state. So to avoid the anisotropic interactions, or to average out the anisotropic interactions, when we do NMR experiments in solid state, the sample is kept in a small zirconia tube known as rotors and spin at an angle with respect to the main magnetic field. So if the magnetic field is applied in this direction, the sample will be in a small rotor, and that is placed at an angle. That angle is 54 degree 44 minutes. And then this sample will be spinning along this axis so that these anisotropic interactions are averaged out. As we spin faster and faster, these anisotropic interactions will be removed, and we will get a solution type spectrum. So for example, here I'm showing the magic angle spinning spectrum of the phosphorus spectrum of barium diethyl phosphate. Barium diethyl phosphate has only one phosphorus, so ideally we should get only one chemical shift or one peak. But as you can see here, you are seeing multiple peaks. So if we are not spinning the sample at all, you will get a peak which covers this envelope. And as I start spinning faster and faster, you can see that this particular peak remains in the one chemical shift, and rest of the peaks spread out. These peaks are known as spinning side bands, and as you spin faster and faster, they will get removed, and ultimately you will remain with one single peak corresponding to the one phosphorus isotropic chemical shift. So all the experiments which I have shown before, like 1D, 2D, and correlation experiments, everything can be done in solid state also, but those experiments will be under the magic angle spinning conditions to remove the anisotropic interactions. And this, to remove the anisotropic interactions completely, we have to spin fast. And the rate at which we can spin depends on the size of this rotor we are using. Nowadays, people typically use rotors ranging from 4 millimeter in diameter to as small as 0.9 millimeter. So if I have a 4 millimeter rotor, I can spin the sample up to 15 kilohertz. Whereas if I have something like, say, 1.3 millimeter rotor, I can spin the sample up to 67 kilohertz. So these kind of experiments are always known as magic angle or MAS experiments. So all solid state experiments are performed under magic angle spinning conditions to remove anisotropic interactions. Now, I know that this is not a sufficiently good introduction to NMR, but I want to talk about something else in this seminar, which is a dynamic nuclear polarization. So the advantage NMR has other spectroscopic technique is its resolution. The lines are pretty sharp, and even minor changes in the chemical environment will be reflected in the NMR spectrum. So it is very easy to use it for structural identification of the molecules. But the disadvantage is its poor sensitivity. So compared to other spectroscopic techniques, the NMR has a very low sensitivity, and the sensitivity in NMR is usually represented in terms of signal to noise ratio. And the signal to noise ratio is proportional to the magnetogyric ratio, gamma, which is inherent for a nucleus, so we cannot do much about it. And B0, which is the external magnetic field applied. That magnetic field we can vary. As I said earlier, nowadays high magnetic field strengths are available up to 1.2 gigahertz. That will correspond to approximately a magnetic field strength of 28 Tesla. But there are limitations to increase this magnetic field strength. So one of the main research topic in NMR is to how to improve the sensitivity. And there is a method known as dynamic nuclear polarization. What we do in dynamic nuclear polarization is to transfer the electron polarization to nuclear polarization. So if you look at electrons also have a spin, which is spin half, and its gamma magnetogyric ratio is 660 times higher than that of the highest gamma nuclear proton. So if you can transfer somehow this polarization from electrons to, say, protons, then we can increase the sensitivity of NMR by this factor, like 658. And if you consider other nuclei, because the gamma of those nuclei are less, we can get even higher sensitivity. So this kind of sensitivity, what does that imply? Say, for example, if we have an enhancement factor of, say, 100, the maximum we expect for proton is 658, but at least let's hope that we get only 100. Even if we get only 100 at a 500 megahertz spectrometer, that sensitivity will be equal to what we can achieve, or even more than what we can achieve on a 10 gigahertz spectrometer. 10 gigahertz spectrometer, of course, does not exist. But at a 500 megahertz, if we can achieve a sensitivity enhancement of 100, we will exceed the sensitivity that can be achieved on a 10 gigahertz spectrometer. So the idea is to transfer the polarization or the sensitivity from electrons to nuclei, typically protons. We can do this transfer to other nuclei as well. Now, how do we do this transfer? This is done by different mechanisms, there are 4 known mechanisms for transferring the polarization from electrons to nuclei. They are, one is known as Overhauser effect, second solid effect, cross effect, and thermal mixing. Now, like NMR spectroscopy, the DNP enhanced NMR also can be performed both in solution state and in solid state. If you are doing solution state DNP, then Overhauser effect is the mechanism that gives the sensitivity enhancement. Whereas all 4 mechanisms can give rise to sensitivity enhancement in solid state. Now let's talk about these polarization mechanisms. How does this work? So to do this DNP experiments, we have to have a sample which has an unpaired electron, which can give like an EPR spectrum, and then we have to have a nucleus to which we are doing the polarization transfer. So the simplest system, or for an Overhauser effect, we have to consider a two-spin system where one spin is an electron, and the other is a nucleus. So when you have two spins like that, there can be 4 possible energy levels, like where, okay. So if you consider spin half nuclei like proton, the plus half state is the low energy state and minus half is the high energy state. But for electrons, they have a negative gamma, so beta, or the minus half state is the low energy state and plus half is the high energy state. So when you have an electron nuclear two-spin system, there are 4 possible energy levels where both electron and nuclei are in the low energy state, or beta alpha state, and then beta beta state, alpha alpha, and alpha beta. So this is like the plus half minus half, then the opposite, and minus half. So 4 energy states. And in NMR, the M value, the total M value change should be plus or minus. Those transitions are known as the allowed transitions. So in this 4-level diagram, the 4 transitions here, these 2 blue transitions and these 2 red transitions, these are the allowed transitions where the delta M value is plus or minus 1. And these two, since we are considering a 2-spin system with 1 electron and 1 neutron, proton, these 2 blue transitions here, they corresponds to the NMR transitions of the nuclei, and the 2 red transitions that corresponds to the EPR, corresponding electron transition, or the EPR transition. Now EPR transitions comes in the microwave region, whereas the NMR transitions comes in the radio frequency region. Now ideally there are 2 more transitions possible between these 2 levels, where the total delta change for the green is like 2 units. So such transitions are known as double quantum transitions. The allowed transitions, where the delta M value change is plus or minus 1, are known as single quantum transitions, whereas here there is a 2 change in the quantum number, the delta M value. So that those transitions are known as double quantum transitions. And the yellow transitions shown here that is from is actually 0. So such transitions are known as zero quantum transitions. Now the double quantum transitions and the 0 quantum transitions are generally known as the forbidden transitions. It does not really happen when we try to excite it. Now, to get a DNP enhancement, and when we consider a single spin, the spin will be either in the low energy state or in the high energy state. But when we consider an ensemble of spins, some of them will be in the high energy state and some of them will be in the low energy state. And the distribution is dependent upon the Boltzmann distribution law, and the net polarization will be the difference in the populations between high and low energy states. So at room temperature, both high and low energy states will be populated, and the population distribution is dependent upon the Boltzmann distribution law. Now, as I said earlier, these blue transitions are the NMR transitions, and the transition intensity or the signal intensity will depend upon the population difference between these 2 energy levels. Now, to do a Overhauser effect-based DNP experiments, what we do is we give a microwave radiation to saturate these EPR transitions. When we do this kind of saturation of the EPR transitions, that is these 2 red transitions, that will lead to a relaxation processes through 0 and double quantum processes. Now, if a 0 quantum process happens, that will lead to a polarization, the population increase in the low energy state, thereby increasing the probability of the the intensity of this NMR transitions. Similarly, if the double quantum process happens, that will increase the population here, and that will also lead to an increase. But these two are in two opposite directions. So generally, if we have a zero quantum relaxation process, that will give rise to a positive enhancement, whereas if we have a double quantum relaxation process, that will lead to a negative signal enhancement. Now, in reality, in a sample, both zero and double quantum relaxation processes will happen, and whether we see a positive enhancement or a negative enhancement for the NMR signal will depend upon which process dominates. There can be a situation where both of these processes happens and we don't see any enhancement at all. But generally, we will see either one of those the relaxation processes dominates, and we will see either a positive enhancement or a negative enhancement. Now, the solid effect is also a similar two-spin process, but here, in the presence of an electron-nuclear dipolar interactions with high-power microwave radiation, it is possible to excite the quote-unquote the forbidden transitions. And if we can excite the zero quantum transition, that will lead to a negative enhancement, whereas if we can excite a double quantum transition, that will lead to a positive enhancement. So both Overhauser effect and solid effect are two spin processes, and depending upon which is the dominant relaxation mechanism, we will see either a positive or a negative sensitivity enhancement in the NMR spectrum. Now, the third relaxation, the DNP mechanism is known as the cross effect, which is unlike the other two processes. This is a three-spin process. So the three spins involved are 2 electrons and one nuclei. And when you have 2 electrons, the condition to get cross effect is that the EPR transition frequency difference between these two nuclei has to be, between these 2 electrons has to be equal to the NMR transition of that nuclei. If this condition satisfies in a 3-spin system of the 8 energy levels present, these 2 energy levels become degenerate. And again, depending upon whether you give the microwave radiation on the high field, the low field line, or the high field line, you can get either a positive or a negative enhancement. Now, the fourth effect, which is known as the solid effect, is a multi-spin process, and it is not generally observed at normal temperatures. It is observed only at extremely low temperatures, and it's not generally used. Now, you may not have understood everything that I have said, but one thing that you might have noticed is that to do a DNP experiment, the sample has to have a free electron or a radical in it. But normal NMR samples are diamagnetic. They don't have any paramagnetic species in there. So we cannot do DNP without an electron spin in the sample. So to do DNP experiments, the normal NMR samples has to be doped with a radical, which can give rise to an EPR spectrum. So since both Overhauser effect and solid effect are 2-spin processes involving 1 electron and a nuclei, monoradicals like TEMPO or galvanoxyl, or such radicals like there are a number of radicals available. Some of them are shown here. These can be used for solid effect based DNP or Overhauser effect based DNP. And we have seen that cross effect needs 2 electrons. So we have to use biradicals, which have 2 electrons for cross effect based DNP experiments. So to do DNP experiments, we have to mix this sample with our NMR sample with a radical and then use it for experiments. Now I want to talk a little bit about the spectrometer, the DNP spectrometer. So the DNP spectrometers is a combination of an EPR spectrometer and an NMR spectrometer. it has to have both microwave and RF radiation capabilities. So people do these DNP experiments in two different ways, either based on EPR instrumentation with additional NMR capabilities, or based on an NMR spectrometer with additional EPR capabilities. So this is the picture of a W-band DNB spectrometer at IIT Madras in Professor N. Chandrakumar's lab. Here you can see the W-band magnet, and here this is known as the console where all the microwave generation, RF generation, everything happens, and those are transferred to the sample inside, kept inside that magnet. So this is an EPR-based system with additional RF capabilities. Now in magnetic resonance, which includes both EPR and NMR, a cavity or a resonator or a probe that refers to the part of the spectrometer which actually holds the sample and delivers the microwave or the RF power to the sample, and then picks the signal that is coming from the sample and sends to the rest of the electronics for amplification and detection. So this resonator or the probe has to tune to the required frequency. So for example, this probe or the resonator can be compared to a radio. If you want to listen to a specific RF station or the radio station, you have to tune your radio to that particular frequency. Similarly, the probe or the resonator has to be tuned to the required frequency to take the NMR spectrum or the EPR spectrum at that specific frequency. So since our DNP experiments involves both EPR and the NMR radiation or the NMR excitation, we need to have both RF and microwave capabilities, and the probe ideally should tune to both, or should have a resonant circuit or to both RF and the microwave. Now there are such probes available, especially like the Endor probes, which are both resonant circuits to both the radio frequency as well as the microwave. But the problem with the microwave resonant cavities is that as you go to higher and higher field, the size of the cavity reduces. For example, X band, which corresponds to an NMR frequency, proton NMR frequency of say 15 megahertz, and the EPR frequency of 9 gigahertz, the cavity can accommodate a tube of 4 millimeter size. But as you go to higher and higher, say like to the W band, the resonance frequency, the proton resonance frequency is close to 145 megahertz. And the EPR frequency is like 90 gigahertz. So this size, then in this resonator, the size of the sample reduces to something like less than 1 millimeter diameter sample, the tube, NMR tube. So it is not really possible to use such small tubes as we go to higher and higher NMR frequency. So when we go to high field DNB experiments, we generally tend to use probes which are resonant only to NMR, not to EPR. So based on the resonant cavity, the NMR probes or the resonators are categorized into two, which are like double resonant cavities, and which are used typically at low magnetic fields up to say 140 gigahertz, but and 200 megahertz NMR. But if you are going to do the higher and higher field, then we use resonators or the probes which are resonant to only to the NMR frequency, but not to the RF, or not to the microwaves. So now let me move on to some results. How do we do these DNP experiments? So I have done both solution state DNP as well as solid state DNP. The solution state DNP is based on the Overholser effect, and typically we did fluorine DNP experiments at various fields ranging from X, Q, and W band frequencies. So fluorine is a highly abundant nuclear, like 19F, and these experiments, so fluorines, they are a little bit special. So if you do a DNP experiments on a proton sample, typically the dipolar interactions dominate, which means that you typically have the double quantum based relaxation processes and you get a negative enhancement. So that's what we are seeing here. So this is how a standard NMR spectrum will look like without no DNP, very small signal. But when we do DNP with a microwave radiation using a 20 millimolar galvanoxyl sample, you can see that you get a proton enhancement, which is negative, and it is enhanced, or the signal intensity is improved approximately by 60 times. But as we go to higher and higher field, so this particular spectrum was collected at the X band with a proton resonance frequency close to 15 megahertz. Whereas this one, it is a W band spectrum where enhancement goes down. This is because the dipolar interactions, which leads to the double quantum relaxation processes, goes down as the magnetic field increases. So the enhancement goes down. But fluorine, unlike protons, has both scalar and dipolar interactions, which means that both double quantum and zero quantum relaxation pathways are active. And unlike the dipolar interactions, the scalar interaction based enhancements remains the same as we go to different magnetic fields. So for example, here I'm showing the enhancement, fluorine enhancement at X band, which is like, we get a factor of 20 approximately. And when we go to higher magnetic field, like W band, we still get that kind of enhancement. This is because the scalar interaction remains the same, but the dipolar interaction goes down. But so ideally, we should expect a higher enhancement at a higher field, but we are not saying that just because we didn't have enough microwave power at higher fields. And also, it is dependent upon the kind of radical we are using. Usually, radicals which have a electron density which is localized to a specific nuclei shows negative dipolar enhancements, whereas delocalized electron density in a radical like galvanoxyl leads to positive enhancement. So in the same molecule, if you have different chemical shifts in the different chemical shift positions, we can see different enhancements. The enhancement values may be different, and even some places you will get negative enhancement, whereas some other chemical shifted positions, you can see positive enhancement. For example, in octafluorotoluene, you can see that when we use tempo radical, we see a negative dipolar enhancement at the CF3 position, but in the aromatic fluorines show negative enhancement, and the enhancement factor at different position is different. But if we use the galvanoxyl radical for the same molecule, the CF3 position now shows very little enhancement, but the aromatic fluorines show higher enhancement, and all of them are positive enhancements. So these are scalar enhancement. But if you use TTBP, you see that there is still negative enhancement at CF3 position and ortho positions, but to para and meta positions, so positive enhancement. So DNP enhancement could be either positive or negative, depending upon the kind of dominant interactions in the sample. And usually we see positive enhancement with delocalized electron density. This is peculiar for fluorine, but for protons, we almost always see negative dipolar enhancements. Now, with this sensitivity enhancement available with DNP, we can do 2D NMR also. So for example, here I'm showing a 2D COSY spectrum that was obtained at W band. You can see that we don't see any cross peaks at all. We are seeing only a diagonal peak. But when we do DNP, we irradiate the sample with microwaves, we can see that all the cross peaks show up. So we have done various kinds of 2D NMR experiments. And for doing this kind of W band DNP, we are using just 2 microliters of the sample. Even high field NMR experiments requires much more sample than that. Typically on a 5 millimeter tube, we use 500 microliters, but these experiments were done with 2 microliters of sample. And we can do these experiments even at X band, which is just 14 megahertz fluorine frequency. And you can clearly see all the cross peaks. So with DNP, we get much higher sensitivity, and using that sensitivity, we can do experiments which are not really possible with the standard standard NMR samples. Now I move on to the solid state DNP. Now solution state DNP, Overhauser based DNP experiments are performed at room temperature on a solution sample with the monoradical. But to do solid state DNP, this has to be at a very low temperature. So we typically do these experiments at 100 Kelvin or below. This means that when we take the samples to such a low temperature, especially if the sample is like a biological sample like protein or temperature sensitive, we have to cryoprotect the sample. So to do such DNP, we use typically a matrix. That is, the sample will be dissolved in a glycerol D2O water mixture. This is a well-known cryoprotectant, or there are other cryoprotectants also. So this is just to protect the sample. Now, even if there are samples which does not need a cryoprotection, even in such situations, we have to use this kind of a matrix to do solid state DNP, because we need to homogeneously distribute the polarizing agent. And this matrix is necessary for an efficient polarization between the electron and the radical. So to do solid state DNP, what we do is we take the sample whose NMR spectrum has to be a sensitivity improved. So say in this case, this is our target molecule, say a protein. So that is, we want to get a better sensitivity NMR spectrum for that protein sample. So this protein sample will be dissolved in a mixture of, say, glycerol, which is a deuterated glycerol, and then D2O and water. And then there will be a biradical also inside that. And the whole mixture will be cooled down to such 100 Kelvin, and then this will be like a solid matrix. And then we do the standard solid state NMR based DNP experiments. So we give the microwave radiation to excite the electron spin transitions, and then the polarization will be transferred to the target molecule to get a better enhancement spectrum. So to do this, and these experiments are typically performed at a high fields, not the solution state DNP experiments which I showed, where the highest field we have done were like W band. But when we go to higher and higher field, we need, as I said earlier, these are non-resonant cavities or non-resonant probes that which we are using, which means that we need much higher microwave radiation at high field solid state cross effect based DNP systems. So instead of the solid state devices that we have used in low field DNP, we have to use a special device known as gyrotron to generate the microwaves with such high frequency and high power. So this is the DNP NMR spectrometer that is that we have built. This is a home built system at MIT. And here you can see that this is the standard NMR magnet. Okay, this is a 500 megahertz NMR magnet, and this is the gyrotron magnet. And the gyrotron is here. It is kept inside that magnet. So the microwave is generated here, and this NMR sample or the DNP sample is placed inside this magnet. And the probe is inserted from the bottom. So this is the probe base, you can see right here. And the sample goes somewhere in the middle of the magnet where the probe goes in. The microwave that is generated at this gyrotron is transferred to the NMR probe through this yellow colored transmission line. These are known as waveguides. These are corrugated waveguides to minimize the transmission losses, and it's transferred and it gets joined at the back of the probe. And to cool the sample down to 100 Kelvin, we use cooled nitrogen gas. So there is a cooling system here, which is not there in this picture. That's all usually known as heat exchangers. So nitrogen gas will be cooled down to 100 Kelvin by passing it through liquid nitrogen. And then that nitrogen gas is given to the probe to spin the sample at 100 Kelvin. So that's how we do the DNP experiments. Now, one of the main focus of my research at MIT was to develop DNP probes for solid state DNP at 500 megahertz. So we have developed two probes, which are known as transmission line probes. I am not going into the details, but if somebody is interested, you can always look at my paper, which we have published here. So this is a triple resonance balanced transmission line probe. The probe looks something like this. The sample, when we drop from the top of the magnet, it goes and sits inside here, and it spins at magic angle here. So this is a home-built probe with our own design. We have designed it in a software called Inventor and then machined it in the central machine shop of MIT. So everything is home-built. And this, unlike the commercial probes, has a modular design. What does that mean? That means that every part in this probe can be removed and replaced with some identical parts. So this is pretty useful because when we build probes, to characterize them, we have to measure various parameters. So when you have standard electrical systems like normal electrical systems, when you want to characterize them, you measure either the voltage or the current. But when we go to higher frequency, like the 500 megahertz or the microwave frequencies, it's not easy to measure current or voltage to characterize an electrical system. So we need to characterize using a set of parameters known as scattering parameters or T parameters, and there are various parameters. So when we design such probes and all, we have to make sure that it works. So that means we have to characterize it by measuring these scattering parameters. And usually when these probes have this problem that once we built an equipment, this is like one piece of equipment, you don't have access to different points within that equipment to make any characterization. So when we have this modular designs, is that you can simply remove one part. So for example, I can remove any of these boxes and then attach a connector there and do the measurements like S parameter or any other characterization parameter, and make sure that the probe tunes to the required frequency and works very well. So another thing is we can swap every single part in this probe. For example, if you buy a commercial probe, if you want to use a 4 millimeter rotor, you have to buy a probe. And if you want to use some other rotor, like say 1.3 millimeter, you have to buy a second probe. But in our design, every part is removable. So we just have to remove the top part, which accommodates the rotor, and then rest of the probe can remain the same. So because we have a swappable design, every part can be replaced with equivalent parts, and we can use this one and same probe for multiple users. Or if you want to use the same probe for different frequency other than the design frequency, you just have to remove the bottom part and replace it with the new frequency circuit. It will work. So this way, a swappable design is good, that it can be used as, it is as good as multiple commercial probes. So here, this is a magic angle probe that we have designed. The sample goes in. If you look closely, you can see the RF coil, which is a solenoid coil. That is what picks gives the RF power to the sample and picks the signal that is coming from the sample. And then it is kept at a magic angle, and then the air, the nitrogen gas comes through these Teflon pieces and spins the rotor. And the microwave microwave is coming right here, and that will hit right here. So it will go to the sample. And these are various parts. So the nitrogen gases goes in through this, and when the sample spins, we have to detect how fast it is spinning. So these detection cables, temperature sensors, all those things are going in. And these are the kind of ports where interconnects different parts of the probe, and we can use these kind of adapters, which again we have designed to characterize the probe. So we have built two different probes. One was a triple resonance carbon proton nitrogen probe, and the second one was a phosphorus proton and nitrogen probe. So this was the results I got on the probe that I have built. Like it works very well on the phosphorus channel, and it can give DNP enhancement also. You can see the enhancement I got was something like 43. So one thing I forgot to mention, initially I mentioned that these rotors are made of zirconia, but zirconia has a problem. It will not allow the microwave to penetrate very well. So to do DNP, generally people use sapphire rotors. Sapphire is a material which will allow the microwave to penetrate much better. But these experiments, I used zirconia rotors because I didn't want to break the sapphire. If you use sapphire rotors, we typically get 20% better enhancements. Now, why do we need this DNP? So what are the typical applications? It is usually used in both in material science to detect pharmaceutical polymers, zeolites, etc., especially for species which have very low concentration. Like many people modify the surface of their catalysts to improve the catalytic reactions and all. Since those materials which are coated on the surface are very low in concentration, it is very difficult to detect using standard DNP and NMR experiments. So people use such kind of samples with DNP, and we will be able to see the signal intensity with much better sensitivity. Similarly, we can use that for biological systems also. So here I'm showing the carbon-nitrogen correlation experiment, which we obtained on an RNA sample using our home-built carbon-nitrogen proton probe. So it can be, so if you do this experiment on a standard NMR spectrometer, it will take days to collect such a spectrum, but this spectrum was collected with DNP just in 2 hours. So that is the advantage. You can get an NMR spectrum much faster than what we can do using a standard NMR experiment. But this sensitivity enhancement also comes at a price. When we improve the sensitivity, the resolution, which was always very good otherwise, goes down. So for example, you can see here, thus, as we go to lower and lower temperature, the DNP enhancement increases. So the cross-peak intensity becomes better and better, but the lines become broader and broader. Here you will see, so for example, by looking at this spectrum, somebody who knows NMR will immediately say these are the isoleucine signals. But as we go to lower and lower temperature, isoleucines are still observable, but you see this some peak here, you cannot distinguish anymore. They are all merged. The sensitivity improves, but the resolution goes down. So one of the main problem we face nowadays, especially in biomolecular DNP, is how to improve the resolution. One thing is, of course, the best thing is to spin faster. That will always improve the signal intensity. Now, another approach we tried is that, see, I said that we have to dissolve the sample in a DNP juice or the DNP matrix to do the cryogenic mass DNP. which means that the sample is actually not a crystalline sample. It is more like a frozen solid. So one approach is that if you make it a rigid crystalline sample, the sensitivity improves. So one approach we have used is that take a protein and cross-link it. That will make the protein like a protein polymer, and it will make nice crystals. So you can see here that this is a standard protein crystal. And when you cross-link it, it forms a shift base, and so it becomes yellow in color, and then it does not dissolve in the DNP juice, the DNP matrix. So this remains as a crystalline sample even at low temperature. And you can see here, this is one of the spectrum that I have collected using my own cross-linked lysozyme sample. Another problem in biomolecular NMR is that if you want to do a protein NMR experiment, typically people always label the samples with C13 and N15. So this experiment was done still with an N15 labeling, but the carbon was still at natural abundance. So which would not have been possible without DNP. So basically we have, in summary, I'm just trying to show you the advantage of DNP using low field fluorine experiments, as well as we have designed and characterized some new instrumentation, especially balanced DNP probes for 500 megahertz, for applications at 500 megahertz. And also I showed some cross-linked DNP spectra. So basically, or in summary, the advantage of DNP is to improve the sensitivity of NMR experiments. And to do this, we have to dope the sample with some radicals and irradiate with microwaves before doing a standard NMR experiment. So with that, I would like to thank some people, especially Professor N. Chandrakumar, who was my PhD supervisor and introduced me to NMR and DNP. I also did a postdoc with him after my PhD. And then I did a postdoc with Professor Bob Griffin at MIT. And I want to thank Bob, as well as Dr. Marcel Rees and Dr. Chen Yang. Those two people worked with me, and also the Penn State University NMR facility where I work currently. With that, I'm stopping my presentation. But I want to talk briefly about the opportunities in US too. So let me, after that, if you have any questions, probably you can ask me, but let me finish that also. So let me go to the internet now. How do I share an internet? Okay, right here, share. And Zoom on. Okay, so I understand that most of you are BSc students, and there are some master students too. Those who would like to come to US, there is a difference in the system in US and in our country. We have this, after the higher secondary, we have bachelor's, master's, and then PhD. That is a typical path. But in US, they have the basic, the general path is like, after the higher secondary, you have a undergraduate education, which is equivalent to our BSc, but this is a 4-year course. And then they have a graduate school, which is like our PhD program. So after the undergraduate, they directly go to graduate school, which is the PhD. They do, some universities do have a master's program, but only some universities, and that too some areas, all the subjects. For all the subjects, they will not have a master's program. So if you have a 4-year BSc degree, the bachelor's degree or the undergraduate course, then you can directly go to PhD program. Now, in our country, since we don't have a 4-year bachelor's program, you have to have a master's to apply for a PhD program in US. Now, if you have by any chance a 4-year bachelor's degree, like the ones that is given offered in ICERS, then you can directly apply for a PhD program or the graduate school. So that way you can save 1 year. But since you are already in the bachelor's program, that may not be an option. So you want to apply for a PhD program, just go. So for example, what are the requirements? For example, I'm just going to the MIT website, just go to the MIT website and then you can click on admission and aid kind of thing. The undergraduate education, you don't need that. That is the bachelor's degree program. Then the graduate admission and aid. So if you click on graduate admissions, it will show you the details, how to do, what are the requirements. Now, since we will, so there are some, if you go to the graduate school, you will see that there are doctoral degrees and master's degrees available. So, but if you look at the master's program, you will see that it is available only in certain areas and chemistry is not included, but there is a chemical engineering, that's the closest you have. But for doctoral degree, you will see the chemistry is there. So you can apply after your master's for a chemistry PhD program. So that is a field of study. And then fields of study, let me go back. If you go back to the applications, procedures, it will tell you what are the eligibility requirements. Now, as an international student, if you want to come here for a PhD program, you need to prove your proficiency in English. So either you have to take a TOEFL or an IELTS course. Now, the requirements, this is the general requirement for every single university in US. The first thing, you must have either a 4-year bachelor's degree or a master's. After, along with that, you have to produce an official GRE test score. So GRE is something like graduate, it's called graduate record examination. It is it has 2 different types of set. There is a general GRE and then there is a subject GRE. So general GRE is required. Subject GRE, if you have it, it's good. And there are some institute which does not require GRE, but they will always prefer people who has a GRE test score. So the most, so if you are planning to, if you are interested and planning to come to US, not just to US, but also this is valid for Canada. And I think for some other English speaking countries also, you may need GRE. So the first thing, you have to take a GRE exam, either an IELTS and TOEFL exam. These are the 2 tests that you have to take to come to US for a PhD program. And depending upon your GRE score, so each school will specify what is the required GRE score you need to apply to that school. So first you write a GRE exam, a general GRE, and if possible, a subject GRE also. And then based on that score, you can apply to. Then the other thing you need is a letter of recommendation. If you are applying to a specific field, it is better to get recommendation letters from people who are experts in that area. But that may be difficult for people who don't have a research experience. So what I suggest is nowadays many academic institutions in India like IITs, ISS, they offer summer projects. Yeah, summer projects and other project options like few months. So if possible, people go there, see what kind of research are going on there and what kind of, sometimes we think that we like some area, but actually when we go to the research program, we may not really like it. So you need to find out what is your interest by seeing some kind of research background. So those who are in the first year or second year of MSc, during your summer vacations and all, you can go for the summer projects. They even offer a fellowship for that. So you don't have to spend anything from your pocket. Go there, do some, see the research and decide what is the kind of area you want. And that will help you to get and if you do nicely there, they will give you a recommendation letter also. And you also may need to get some recommendation letters from your professors who teach you courses, like to see how good you are. So your admission will be mainly, the most important thing is the GRE score. Then you have to pass IELTS and TOEFL or TOEFL. And then your recommendation letter is very important. And then you have to write something called a statement of objectives. And this is like why you are interested in certain field, or what is your goal, something that you have. There are plenty of models available in the internet. You can take that and write like that. Then of course you have to produce your CV and transcripts. And each school has an application fee, which is not much. It's like $75. But for GRE and TOEFL, when you are applying for them, there is an application fee. But I checked, it was less than $200. So these are the two important expense that you will have when you are applying for these things. So prepare for GRE and then apply. Nowadays, if I look at Penn State University, at least 30% of the students are international scholars. So it's not like the old days. It's pretty easy to get admission if you have a good GRE score. And always try to go to the best possible institute with your, so each school will specify what is the required GRE score. Based on that, whichever is the best you can get, go to those schools. And this is not just for the MIT, it is for all institutions. This is the requirement. Now, as you go to lower and lower schools, the requirements becomes less stringent. And nowadays, I heard that some schools are getting even not when considering people without GRE, but that's not for sure. So you have to do a GRE if you ask me, because they will always prefer people with GRE. And all you need to do to apply is, everything is online nowadays. So if you go to the applications, programs, field of doctoral study, if you click on chemistry, there is an application deadline. Okay, so if you are planning to apply for next year, you have to start at least a year before. So when you are in the third semester, for example, or in the first few months of your second year of MSc, you have to start the application process. So there is a link here. You just have to click there, and then it will ask you to log in. So you have to create a login ID and password and then apply. This is same whether you apply to MIT or any others, any MIT, PS or Penn State or to Harvard, wherever you want. All you need is an internet connection and a computer and an internet connection. You can do everything on your own. You don't need to depend on anybody else. And it's better you do yourself. The only problem you may face is that and for PhD, you will always get a fellowship. So all legitimate US schools will, if you are joining for a PhD program, you will be offered a fellowship which will be enough to cover your expenses. So if somebody is offering you a position without a fellowship, don't take it. That's not worth it. And what else do I need to say? That's all, I think. And everything is clearly, and one more thing I want to say is, don't go to some agents and all. You can do everything on your own. They will charge you a lot of money and say all kinds of things which are not necessary. The problem is, even after you get an admission, there is a chance that you will be denied visa at the consulate office. So if you unnecessarily spend a lot of money, I don't think it's a good idea. Now, if you are coming after a PhD, like for a postdoc, you don't need any test, nothing. You just need to apply to the professor in an area where you are interested. And if they have funding, they will send you all the documents. You can come. You don't need any test after PhD. Now, you can technically come for graduate school also, but the graduate school is extremely expensive and only rich people can afford. But if you are rich and as interested, there is you can go back to the main thing that you will see the undergraduate education, but how much it costs and all those things. If you have any questions, you can ask me now. Hello?
Yes, please ask questions if you have.
Stop share. Oh, what?
Yes. Christy, is it audible there?
Oh, yeah, yeah.
Yeah. I'm asking students to ask questions.
Okay. They may have to unmute if they have to.
Yes, they can unmute.
Okay. Oh, there is something in the chat box, I guess. Oh, sorry, I didn't see your Dennis. Sorry,
Yeah,
I
I
didn't see.
reminded time. I think the topics you
I didn't
covered
know
are
what was
mostly.
the. I wanted to say because if I go too much into the research stuff, people may not follow, but then I need to present something. I didn't know how to do it. I'm sorry. But if you want any explanation or if you're interested, you can always send me an email. I'll answer.
Yes.
Okay, I think they don't have any questions.
Most of them are degree students. They might not have heard about all these things.
Yeah.
Many students are degree students.
Mm-hmm. Yeah, they will learn about, I think,
They will.
only in the third year or something.
Yes, third year, right?
Mm. Yeah. Okay.
Apart from the research part, they can ask questions about the admissions and so on in the universities there. No?
Yeah,
They can have questions about that.
Yeah, if majority of them are bachelors, first thing is to get a master's. Yeah, if you can go to IITs or ISOs, I don't know whether they have master's course. That will be good. And nowadays, plenty of opportunities are there. I mean, number of seats are increased, so it's easy to get an MSc admission to IITs and IISc. Oh, NC is still there, I guess.
Yes, it seems.
Sir, you have a question. Sahir has a question to you, sir.
Who are you talking about?
Yeah, Sahir wants to ask you for some advice.
Oh,
Yeah.
you would know that I'm not capable of giving great advice. Anyway, whatever. Ask away.
Okay. Okay, so for students, okay. Do you have some advice for his students? That's what he's asking.
Well, I would simply say decide what appeals to your heart and then work hard at it. Lots of resources are available today right here in our country, so you can compete with the best. Subsequently, if you're interested in making a higher degree abroad or a career abroad, the gates are always open for you to undertake that. So there are plenty of opportunities to study hard, to be competitive, and to contribute. If you're doing a master's program in many universities nowadays, there will also be a project involved there. And you could already you start using this project as some kind of a research training. And if you are going to work hard at your project and are also a little bit lucky, maybe you can even publish something. It's not that MSc dissertations or projects are not publishable. So it is really between how hard you work and how closely you interact with your academic supervisor. That usually makes a lot of difference. But above all, for Indian students in general, I think the only thing that I would say, pardon me for saying this openly, with my age, I think I can take some liberties, much senior to all of you guys in this audience, I guess, in age. And therefore, I'll take the liberty of saying that we should not be afraid to think on our own. And it is not just about reading textbooks alone and committing the material to memory. Memory is very important. There is no learning without memory, but while memory is necessary, it is not sufficient. Particularly in the pursuit of science, it is all about applying the principles you have learned and committed to memory to situations that you might find arising in your research endeavor or whatever else. So I guess that will be the broad message, and just have fun. Basically, I think science, and as you go higher up in your education, bachelor's and then master's and then a doctoral or a postdoc or whatever, before latching on to your calling in life, I think it's about having a lot of fun and adventure, because I think research at any level is among the greatest adventures open to mankind, in my understanding. I think it's about having fun. Don't worry too much about amount of money you make or number of papers you publish. It's not about numbers. It's about quality, and above all about your enjoyment and about applying your mind. So I guess that is the main thing. You will find your own ways to clear competitive exams and get through the admissions process, which is always a rat race, also in the Western world, no less than here in India. Okay, because there is a SAT, for example, in the US. Maybe Christy can tell you more about it. Like we have various exams here, a SAT and a CAT and a GMAT, and for various disciplines, even including management, not to speak of GRE and TOEFL and AELTS, or a NET and a GATE here. So there are always competitive exams. But I think the key is to have fun and understand the principles and not be afraid to apply the principles. Research is not everybody's calling. Some people may be interested in research as a career, in which case you should be willing to work extremely hard and cut your social life very strongly and become very unpopular in your social circle, and not bet on making too much money. But on the other hand, it is up to you. You can say that if you're very inventive in your research, maybe you can make a lot of patents. And if your patents are the technology based on your patents is saleable, you can make some money there as well. The magnetic resonance imaging field, MRI, the people who came up with the initial MRI experiments went on to win the Nobel Prize, but I think they won much more money out of their patent royalties. I hear that Peter Mansfield, who was one of the two MRI Nobelists in 2003, made 70 million pounds from his patent royalties. Whereas, the Nobel Prize is only about $1 million. And if there are two laureates in a year, they usually split it in two. So each gets $500,000. So you compare $500,000, which may be less than 400,000 pounds, and this man made 70 million pounds from patent royalties. So you can make money, but I think the prime motivation is fun. So I think people who are not afraid to have fun and adventure in their laboratory, if you are an experimentalist, I think you can consider yourself as having a fair chance at research. Then just work hard. There is no getting away from working hard. You have to go through the competitive exams. There is no getting away from that either. But then down the line, you put the hard work. It's a kind of a labor of love. Okay, so if you enjoy what you're doing, I think it's a labor of love, and then you have a much better success rate, presumably. I suppose that's what I can say in general. My whole career has been made in India, so I cannot advise you too much about the American scene or insisting. I did spend some stints abroad, but that was probably after my doctoral work and after setting up my own lab in CSIR much later. I was visiting professor in a few places in Europe and briefly also in the US and so on. But uh, I think Christy has better experience about working abroad than I do. I think Dr. Christy George must have now completed, she must be probably in her 7th year abroad. I think in all my career, I spent about 2.5 years abroad in all. So that's not much I can tell you specifically about working in the US. I can only tell you about having fun in what you do. But you don't have to, all of you, decide that you want to do research. You may want to do other things. So, I mean, feel free, whatever is your interest, I think you pursue it with the best of your abilities and the best of your efforts. And nothing is greater or lesser than anything else. Nowadays, there is opportunities galore in everything that you can name. The world is a large place, so there's plenty of room out there for good people. Only thing is, by applying your mind, you will add value to whatever you're doing, and then you will be a champion, no matter what you have decided to do. I guess I guess that's about what I have to say in general, unless somebody has specific questions. But probably about working abroad, I think Dr. Christy George will be in a far better position to advise you. Thank you.
Okay.
Thank you very much, sir. That's great words. Those are great words.
Pleasure. Thank you.
I think if there are no questions, now let me move on to the next session, concluding session. So I request Jason sir to come forward.
Okay, Sahib. Good evening, all. This was a very eminent and interesting session about the advanced field of our NMR. So, as a concluding session of this event, I would like to extend my gratitude on behalf of the Department of Chemistry, KMM GWC Kannur. I would first like to thank our guest faculty, Dr. Christy George, for explaining the basics and the advance of this enhanced NMR spectroscopy. Even though each and every aspects she discussed would not have been digested to us, but still she has opened a window to the advancement in the NMR spectroscopy field. So on behalf of the entire fellow participants over here, and on behalf of the Department of Chemistry and the college KMM GWC Kannur, I extend our gratitude to Dr. Christy for accepting our invitation, especially through Dr. Sahir, to have such a interesting and great session tonight. Thank you, Dr. Christy. And we have blessed with the presence of Dr. N. Chandrakumar sir, the eminent professor from IIT Madras, and we have heard of him through the different teachers we worked with, and he had delivered a very great, inspiring advice. I would like to call advice, because surely I believe that words will benefit our students, especially our students, to come up with their dreams and to pursue the science, field of science. So on behalf of the entire fellow participants over here, I would like to thank our dear Chandrakumar sir for his blessed presence. And not last, at the end, I would like to thank our principal ma'am, our Fatima teacher, our Lega teacher, our HOD of department, all our fellow participants for participating in such a great event. So we will be having this series continuing next week onwards also. So I would like to thank on behalf of the department, on behalf of our college, I thank all the fellow participants over here. Thank you. Over to Sahir, sir.
Thank you, Jason. I think now we can conclude here, right? Thank you very much, Christy, especially and Professor N. Chandrakumar. Thank you, all participants.
My pleasure, and
Thank you.
congratulations on conducting such a program. I really would like to felicitate you on taking this initiative at the college level, which I think is extremely important. because I think your kind of efforts, and you said this will be followed in the coming weeks also, these efforts to expose your bachelor's level students to research at the forefront, if I may call it that, I think this will go a long way in inspiring your young students to thinking along these lines of scientific research and being unafraid to contribute in their time to such efforts as they go along. So I think I would certainly like to felicitate Dr. Sahir and your college, your institution, for constructing such a program and bringing it to fruition and rolling it out now and continuing with it in the weeks to come. All the best to you. Congratulations once again and all the very best.
Thank you. Thank you very much, sir.
Thanks, Sahir. Thank you.
Thanks, Dr. Christy George, as well.
Okay, it's yeah, I think
And now we can exit here, right?
yeah,
Thank
we can
Thank you, Crystal.
yeah.
Thank you.
See you. Bye bye.
Yeah, bye.